Hi, our presentation will be on code-related metrics as indicators of sustainability. Next. So what exactly is sustainability in OSS projects? Sustainability is basically to ensure long-term maintainability, usability, and adaptability. Increasing sustainability would create a significant improvement in the process of software development. But there's a as the code complexity increased, it become harder to keep tracks of the sustainability. Next slide. Our focus is mainly on applying metrics to OSS projects to understand the key factors that impacts the sustainability. Some of the research question we'll be trying to answer are factor that affects the code complexity, relationships in the size of OSS projects and the complexity, and also the version control practice, the code duplications, and the number of contributors, and all kinds of factors that how do they interact or infect our OSS sustainability. Next, please. So the method will be building on psychromatics complexity and cognitive complexity to analyze OSS ecosystem. And we choose to use psychromatics complexity because we want to count path by the source code for a structural aspect on debugging and testing. And we also use cognitive complexity to measure mental effort required to understand code. And this will help us find out developers' comprehensions challenge during the maintenance. Together, we'll review how hard it is to debug, to test, and to understand a OSS projects. And the tool we're going to be using is GENS CPX for calculating psychromatics and cognitive complexity. We'll be using GetSizer for understanding patterns like size. And lastly, we'll compare the complexity metrics across different OSS projects. Next slide. But before that, we'll want to understand three papers that is highly related to our projects. The first one will be about psychromatic complexity, and we'll be using it for a structural complexity and testability analysis, and it will provide a baseline for analyzing OSS project and complexity. And also, we'll use a paper on cognitive complexity, and the paper focus on introduce cognitive complexity as a measure of understandability and complementing the psychomatic complexity. And this will help us evaluate code maintainability, which is a key factor of OSS sustainability. And there will be also one paper about early participations in GitHub projects. The study would be about how early team dynamics and contributors' engagements influence OSS project success. And this would add insight into non-code aspect of sustainability, such as team dynamics and contributor onboardings. Next slide.
In this paper, McCabe introduced cyclomatic complexity. It's a systematic way to assess and manage program complexity. Next, it calculates the number of independent paths in a program's control flow graph. It's not just a number, it's also an essential tool for better understanding the logical structure of software. It emphasizes it emphasizes the importance of focusing on decision structures and help us to analyze complexity in OSS projects. Cyclomatic complexity is calculated using the formula V equals to E minus N plus 2P, where E is the number of edges, N is the number of nodes, and P is the number of connected components. For a single program, P equals to 1. Since the calculation can be quite tedious, there are two ways of simplification. The first method simplifies V to pi plus 1, and which means that the cyclomatic complexity of a structured program is simply the number of predicate nodes plus 1. And the second method uses Euler's formula, since the number of regions in the connected plane graph is E minus N plus 2, so we can simply do the calculation by counting the regions. Next.
So cyclomatic complexity is important since it helps us focus on the decision structure rather than just the code size. The programs with high complexity values, for example, above 10, are harder to test and maintain. And refactoring them into smaller, more manageable modules can significantly improve quality. Cyclomatic complexity also serves as a guide for testing, ensuring all independent paths are covered. Next, please. So in our study, cyclomatic complexity serves as a key metric for accessing the structural complexity of open source software, impacting reliability, testability, and maintainability. By measuring independent code paths, it helps identify projects that are difficult to understand, modify, or debug. It also helps in analyzing factors that will contribute to the code complexity, like project size, code duplication, and contributor workflows, offering insights into modularity and long-term sustainability. Next, please.
Next paper talks about cognitive complexity. Next. Even though cyclomatic complexity accurately measures the testability of a code by calculating the number of independent execution paths in developers' programs, it is hard to measure the maintainability. We argue that a project is maintainable if each method of each file is easy to understand. However, as a measure of understandability, cyclomatic complexity is widely regarded as unsatisfactory, but until December 2016, it was the only one available. This gap is what cognitive complexity, which is a metric designed by Sonar Cloud specifically to measure understandability, aims to address. Next. What is cognitive complexity? The cognitive complexity of a code snip is the time required by a human being to understand it. It emphasized the cognitive load placed on developers trying to read and interpret the code. It solves the problem by introducing 3 core rules that align more closely with how humans read and process code. Rule number 1, ignore readable shorthand structures. Constructs like the ternary operator or simple functions are ignored because they don't add significant cognitive overhead for experienced developers. Rule number 2, increment for breaks in the linear flow. Each time the code breaks the linear flow, such as through conditional loops or exceptions, cognitive complexity increases. Rule number 3, increment for nested control flow. Cognitive load rises with each level of nesting, as deeper nesting requires developers to mentally juggle more context at once. Next.
Yeah, so for a metric designed to bridge cyclomatic complexity understandability gap, the most important measure of success must be based on developer responses. So the study used developer reactions on Sonar Cloud and analyzing 8,180 open source projects with the method level cognitive complexity roles across 4 widely used languages, including Java, C#, JavaScript, and C++. By narrowing the scope to 22 projects where developers actively manage cognitive complexity issues, the study demonstrates that the projects largely accepted the metrics, around 77%, highlighting its practicability and reliability in accessing code understandability. Next, please. So by incorporating cognitive complexity, we can better evaluate code bases in open source software ecosystems and identify potential factors that affect maintainability. Next.
So paper 3 is how early participation determines long-term sustainability in GitHub projects. The background is that they want predicting OSS sustainability through early participation. So OSS is critical but struggle with sustainability. And they have 2 research questions. The first is, can early participation predict long-term success? And the second is, which factor matter most? To answer this question, they analyze 290,000 GitHub projects. So reuse model XGBoost, they achieve accuracy of 0.84. And real name for explainable AI. Refined 3 variable measure. The first is willingness, and the second is capacity, and the third is opportunity.
Open source projects often struggle with long-term sustainability, but this paper highlights that early participation is a key predictor of success. The study analyzed about 300,000 GitHub projects and found that three major factors, which are willingness, capacity, and opportunity, significantly impact project survival. First one is a willingness, which refers to consistent contribution from the core developers. And project with steady engagements are more likely to survive, while those with early bursts of activity followed by inactivity tend to fail. Also, non-code contributors, which are people who discuss issues and review PRs, play an important role in sustainability. Second one is capacity, which is about developer experience. Those who have successfully contributed to long-lasting projects are more likely to build another sustainable one. This means maintainers should engage experienced developers, while newcomers should look for projects with strong leadership. The last one is opportunity, which refers to how accessible a project is. And good documentation like README contributing files make it easier for new contributors to get involved. Meanwhile, projects with too many unresolved issues often struggle. Maintaining clear documentation and well-management issues can improve sustainability. And the key observation here is that organizational projects require more experienced developers and stronger team dynamics than individual projects. Next slide, please. This research closely relates to our project on OSS sustainability. While we focus on code-related metrics, this study highlights the human and social aspect of project success. By combining both technical and behavioral insights, we gain a more complete understanding of what makes open source project last. Next slide, please.
Next slide, please. To conclude our background presentations, we explained three highly related paper. The first one is psychometric complexity provide a fundamental metrics for analyzing code testability and modulability. And also cognitive complexity is critical for understanding code maintainability and developers' comprehensions challenge. And also early participation shapes sustainability through strong team dynamics and effective onboarding. Combining these techniques, which include technical metrics and aspects from team dynamics, we will be able to create a complete understanding of OSS sustainability. We'll build on this work to explore patterns, challenge, and actionable insights for OSS maintainability and adaptability. Thank you.